So let's continue with activated carbon. And we looked at various isotherm methods. We looked at linear isotherms. And so now what we want to do is look at how do we apply that in an engineered setting. So there's a number of ways that we can apply activated carbon in an engineered setting, and one of which is to use powdered activated carbon and actually add it into an existing system. Typically, if this is done, it's done seasonally. So for instance, during the summer, when you have more primary productivity, more plant growth in the source water, you're more likely to produce trihalomethanes or haloacetic acids during disinfection. So for that reason, powdered activated carbon may be added within the existing system to absorb some of that organic matter, the naturally occurring organic matter, to reduce the amount of trihalomethanes and haloacetic acids that are formed during disinfection. And we can think of that as being done, for example, in a system where you're adding coagulants. So for instance, if you have a rapid mix system, you add powdered activated carbon with the coagulant, and you waste that powdered activated carbon in the sludge. So your powdered activated carbon with, in this case, the naturally occurring organic matter ends up in the sludge. And shown similarly here, so that those particles, powdered activated carbon, is flocculated and then ends up in the sedimentation. What we're doing is, you can think of this as a soil, think of a soil system. So you have some sort of media, could be soil. In this case, it's activated carbon in a column. So we have some sort of a column here filled with this media, and we're allowing water to flow at a particular flow rate through the reactor. This system does not operate at steady state. It is a non-steady state system. And what's happening is, over time, your particles, your grains of activated carbon, or it could be sediment in a natural system, are absorbing the contaminant. Same thing happens. You can think of this as the Brita filter, or if you anyone have a faucet filter at home. So you have a filter that's actually installed on the faucet. If not,
I used to.
Okay. Basically, what you have is a packed bed reactor. The water's flowing through that reactor, the chemicals being absorbed, and eventually all of the sites would become absorbed. I'm not going to circle all of them, but all of the sites would become what we call exhausted. They would reach their capacity for absorption. So this absorptive capacity is finite. It's still described by isotherms just as we used before. But the difference here is this is not a steady system. So it's not operating at steady state. So what we would see if we plotted the concentration in the effluent, so the concentration leaving here, as a function of the volume treated, and this is C naught, what you typically see is the concentration would be relatively low, and then it would start to increase, and it would reach that initial concentration if you let it go long enough. The amount of mass that you have removed is equivalent to the area above the curve that I've, okay? So this corresponds to the mass. We will also talk about what is referred to as a breakthrough concentration. And that concentration is defined, often we'll refer to it as 0.05, 5% of C naught. However, in actual operation, that is often dependent on a regulatory limit. So it may be, we'll just do all of the designs with 0.05, but the actual breakthrough curve in actual systems is based on a regulatory limit. And then we will also use C exhaust, and that is typically taken as 0.95 times C sub 0. So those are the terms that we need to think about. And the other term that we need to think about is what we refer to as the empty bed contact time. And that is the volume of the bed empty divided by Q. So that term is often used in describing these systems. So what you see here is essentially what I drew before. And so we're breakthrough, what we refer to as a breakthrough curve. So this is C effluent, and it's a function of the volume of the effluent treated. So here's our break pointer, and often used 0.05 C naught, and then C exhaust is typically 0.95 times C naught. Now, the way we describe this is we talk about an adsorption zone. Think of that here as this portion here that I've shown in yellow. If I were to monitor the concentration leaving that zone, it would be C equilibrium. It's the equilibrium concentration. Over time, that adsorption zone moves down the column. So you can see it here. It shows now the adsorption zone here. It's moved down the column. It's moved further down the column. And eventually, it moves out of the column. So eventually, if we run this column long enough, then the concentration leaving would be the same as the concentration entering. Okay, so we've exhausted all the capacity. The time to breakthrough is defined as the height of the bed minus the height of the adsorption zone, so minus the height of that adsorption zone, divided by the velocity at which that adsorption zone is moving down the column. Now, the other terms that we also talk about is a depth of the adsorption zone, and this figure is actually taken from the FE reference handbook. So your depth of your adsorption zone is defined here as Z sub S. The Z is the total carbon depth. And then VT here is the volume required to reach adsorption, exhaustion. Okay, so it's the volume where C equals 0.95 times C0. So that's my effluent concentration. Now, V sub Z is the difference between this volume here, VT, and VB, so the volume to break through. What you want in a column is a sharp breakthrough. Now, if we have a really sharp breakthrough, note this is V sub T here, then VZ equals VT minus VB is small. What that means is that we're effectively using the column. So sharp breakthrough means that means the depth of the absorption zone is small. Okay, and it means this VZ is also small. We also talk about terms of the number of transfer units and the height of a transfer unit. The number of transfer units represents the overall change in solute concentration divided by the average driving. And that we can write mathematically as Y2 as Y1 change in Y over Y minus Y star, where Y star is the equilibrium concentration. The height of the transfer unit is a measure of the separation effectiveness. The smaller the number, the more efficient. The larger the number, if we have a certain number of NTUs that we need in order to achieve the removal, the larger the HTU, the height of the transfer unit, the bigger the column we need. Basically, think of it that way.